Right now, based on what we know so far, if we wanted to name this molecule, we would say, well, what's the longest carbon chain here? Well, we have a 2-carbon chain. So we're dealing, and there's all single bonds. So we're dealing with an ethane. We're dealing with an ethane. Actually, I'll write it all at once. And then we have on the 1-carbon, we could call this the 1-carbon and call this the 2-carbon. We have a bromine and a fluorine. So we could call this 1,1-bromo. And we're putting the bromo instead of the fluoro because B comes before F alphabetically. 1-bromo, 1-fluoro, 1-fluoro. And then we're dealing with an ethane, right? We have a 2-carbon chain, all single bonds, fluoroethane. That's the name of that molecule there. Just a review of some of the earlier the nomenclature videos we had done. Now, we know immediately, based on the last few videos, that this is also a chiral carbon. And if we were to take its mirror image, we would get another enantiomer of this same molecule, or that they are enantiomers of each other. So what does the mirror image of this 1-bromo, 1-fluoroethane look like? Well, you'd have the carbon right here. You would still have, I want to get all the colors right. You would still have the bromine up above. You would have this methyl group that's attached to the carbon now pointing in the left direction, CH3. The fluorine would now still be behind the carbon. So the fluorine would still be behind the carbon. And now the hydrogen would still pop out of the page, but it would now pop out and to the right. So it would now pop out and to the right. Just like that. That is the hydrogen. Now, based on our naming so far, we would name this 1-bromo, 1-bromo, 1-fluoroethane. And we would also name this 1-bromo, 1-fluoroethane. But these are fundamentally two different molecules. Even though they have the same molecules in them, they have the same molecular formula, they have the same, I guess you could call it, constitution, in that this carbon is connected to a hydrogen, a fluorine, and a bromine. This carbon is connected to the same things. This carbon is connected to a carbon, 3 hydrogens. So is this one. These are stereoisomers. These are stereoisomers, and they're mirror images of each other. So they're enantiomers. Enantiomers. And actually, they will, polarize light differently, and they actually will have they can often have very different chemical properties in a chemical or a biological system. So it seems, I guess, not good that we have the same names for both of these. So what we're going to focus on this video is how do you differentiate between the two? Enantiomers. Enantiomers. So how do we differentiate between the two? So the naming system we're going to use right here is called the Cahn-Ingold-Prelog system, but it's a different Cahn. It's not me. It's C-A-H-N instead of K-H-A-N. Cahn-Ingold-Prelog system. Prelog system. And it's a way of differentiating between this enantiomer, which right now we would call 1-bromo, 1-fluoroethane, and this enantiomer, 1-bromo, 1-fluoroethane. And it's a pretty straightforward thing. Really, the hardest part is to just visualize rotating the molecules in the right way and figuring out in which direction it's whether it's kind of a left-handed or a right-handed molecule. We're going to take it step by step. So the first thing you do in the Cahn-Ingold-Prelog system is to, one, identify your chiral molecule. Here it's pretty obvious. It's this carbon right here. It is bonded to, well, we'll just focus on this left one, the one we started with first. It's bonded to 3 different groups. And then what you want to do is you want to rank the groups by atomic number. So if you go up here, out of bromine, hydrogen, fluorine, and a carbon, this is what is bonded directly to this carbon, which has the highest atomic number. Well, you see bromine is over here. Let me do this in a darker color. We have bromine at 35. We have fluorine at 9. We have carbon at 6. And then we have hydrogen at 1. So of all of these, bromine is the largest. We'll just call this number 1. Then after that, we have fluorine. That is number 2. Number 3 is the carbon, number 3. And then hydrogen is the smallest. So that is number 4. Number 4. So now that we've numbered them, the next step is to orient this molecule so that the smallest atomic number group is sitting into the page. It's sitting behind the molecule. So if we were to, right now this hydrogen is the smallest of all of them. Bromine's the largest, hydrogen's the smallest. So we want to orient it behind the molecule. The way it's drawn right now, it's oriented in front of the molecule. So to orient it behind the molecule, and this really is the hardest part, is just to visualize it properly. Remember, this fluorine is behind. This is right in the plane of the paper. This is popping out of the paper. We would want to orient. We would want to rotate. You can imagine if we're we'd be rotating the molecule in this direction, so that, let me redraw it. So that now we have, let me redraw it. We have the carbon here. And now since we've rotated it like this, we've rotated it roughly about one third around the circle, so it's about 120 degrees. Now this hydrogen is where the fluorine was. So now this hydrogen is where the fluorine was. So that's where the hydrogen is. The fluorine is now where this methyl group is. So the fluorine is now where this methyl group is. These dotted lines show that we're behind now. This shows that we're in the plane. And the methyl group is now where the hydrogen is. Now popping out of the page. It's going to the left and out. So this methyl group is now popping out of the page, out and to the left. And that's where our methyl group is. So all we've done is we've just rotated this around about 120 degrees. That's the hardest. We've just gotten this to go behind. And that's kind of the first step after we've identified the chiral carbon and ranked them by atomic number. And of course, the bromine is still going to be on top. The bromine is still going to be on top. Now, once you've put the smallest atomic number molecule in the back, then you want to look at the rankings of 1 through 3. I mean, we have four molecules here. So we look at the largest, which is bromine, number 1. Then number 2 is fluorine, number 2. And then number 3 is this methyl group. That's the carbon that's bonded to this carbon. So it's number 3 right there. And in the Cahn-Ingold-Prelog system, we literally just think about what would it take to go from number 1 to number 2 to number 3. And in this case, we would go in this direction. To go from number 1 to number 2 to number 3, we would go in the clockwise direction. We're just kind of ignoring the hydrogen right now. That's kind of sitting behind it. That was the first step, to orient it so it's sitting in the back, the smallest molecule. And then the 3 largest ones, you just say, what direction do we have to go from number 1 to number 2 to number 3? In this case, we had to go clockwise. And if we go clockwise now, then we call this a right-handed molecule, or we use the Latin word for right, which is rectus. Rectus. And so we would call this molecule right here is not just 1-bromo-1-fluoroethane. This is R. R for rectus, or you can even think right, although we'll see left uses S, which is sinister. So the Latin is really where the R comes from. But this is R, 1-bromo, 1-bromo, 1-fluoro, 1-fluoroethane. That's this one right here. So you might guess, well, this must be the opposite. So this must be the counterclockwise version. We can do it really fast. So same idea. We know the largest one, bromine's number 1. That's the largest of the, in terms of atomic number. Fluorine is number 2. Carbon is number 3. Hydrogen is number 4. What we want to do is put hydrogen in the back. So what we're going to have to do is rotate it to the back to where fluorine is right now. So if we were to redraw it, draw this molecule right here. You have your carbon still. You still have your bromine sitting on top. But we're going to put the hydrogen now to the back. So the hydrogen is now where the fluorine used to be. The hydrogen's there. This chlorine is going to be moved to where the hydrogen now is. Not the chlorine, sorry. This methyl group, this carbon with the 3 hydrogens, is going to be rotated to where the hydrogen used to be. It's now going to pop out of the page, because we're rotating it in that direction. So this is our methyl group right there. And then this fluorine is going to be moved where the methyl group was. So this fluorine will go right here. And now, using the Cahn-Ingold-Prelog system, this is our number 1. This is our number 2, just by atomic number. This is number 3. You go from number 1 through number 2 to number 3. You go in this direction. You're going counterclockwise, counterclockwise. Or we are going to the left, or we use the Latin word for it, which is sinister. And the word sinister comes from the Latin word for left. So it's, I guess right is good, and people thought either left-handed people were bad, or if you're not going to the right, it's bad. I don't know why, sinister took on its sinister meaning now in common language. But it's now the sinister version of the molecule. So we would call this version, this enantiomer of 1-bromo-1-fluoroethane, we would call this S. We call this S. S for sinister, or for left, or for counterclockwise. S, 1-bromo, 1-bromo-1-fluoroethane. So now we can differentiate the names. We know that these are two different configurations, and that's what the S and the R tell us. That if you had to go from this to this, you would literally have to detach and reattach different groups. You would actually have to break bonds. You would actually have to swap two of these groups in some way in order to get from this enantiomer to this enantiomer. They're different configurations, really fundamentally different molecules, stereoisomers, enantiomers, however you want to call them.